Okay, so we're rolling. The first question is, when will we have the midterm? -9 Firefox, let's kill it. Damn. Firefox is not found. What about this guy? Really found. Why is my favorite command no longer working? Do we know? Okay, old-fashioned way, close tabs. Get started over. So let's first take a look at when the midterm can happen. So 238p. We are now, today we're going to start a new lecture or new topic, which will be segmentation and paging. And it will take us a couple of weeks to finish. So essentially, if we are right now doing something like, we started on address translation, right? That will take us the whole week this time. Then we need a yeah, no, wait a little bit for a midterm. Let me announce the schedule. So it's not super hard, but I'll just stitch the dates, but we still need a couple of weeks, right? So it never happens at weeks 5, but 6 or 7 is realistic. Good. Okay, but yeah, so remind me on Piazza and I will come back and answer it. So what I was doing, what we were doing last time, right? And so I wasn't able to teach, and I assigned you and just a recorded lecture about shared libraries, static libraries, and position-independent code. So let me first ask questions. Ask a question if there are any questions about these subjects, right? So we started about here, and we essentially went forward the lecture. The recorded lecture covered everything about static libraries and essentially dynamic libraries, right? And I hope you understood it. But if there is anything unclear, let's stop for a second and clarify it right now. Everything is good? Well, like homework 3 asks you to implement a simple elf loader and actually do some relocation, right? So you better understand a little bit what's going on there. So, which, I mean, maybe you know from previous classes, but what I wanted to talk about a little bit today is that something what wasn't covered in the lecture and what we didn't cover in a previous lecture, right? So essentially, we stopped right around here, essentially, when we were doing this relocation of those relative function calls, right? And we said, okay, this is a relative 3 bytes after the next instruction. So this is exactly how it works, right? So we understood it. But something what we missed is essentially a couple of file formats, which essentially allow us to represent all the object files together, right? So let me quickly recap what's going on, right? So, and again, I hope that most of it is already clear to you, right? And but feel free to interrupt me on chat, and I will stop and explain. So what we've done so far in this class, right? And actually, let me quickly. Okay, it's okay. We can use this one. So what we've done, we talked about basics of x86 assembly. We talked about calling conventions, right? So essentially at this point, we know how to call a function, how to pass arguments. We also know how the object files, binaries, shared libraries, and static libraries are built by the compiler and linked by the linker, right? And just to recap, I wanted to quickly just draw another figure just to make sure that everyone conceptually understands what's going on. So if you start your project with something like a C file, right? You invoke a compiler, something like a GCC, for example, right? and it produces an object file, right? And you typically have a tree which contains a bunch of these C files, right? So something like foo.c, bar.c, and maybe your main file, which I mean you can call main, but it's not a like it's just a convention, main.c, right? And we use make files to essentially, as a build system, to essentially say, okay, please, if you see something like a C extension, please invoke a GCC compiler. So something from .c, we go to .o by invoking a GCC compiler with some flags, and essentially we will produce an object file, right? So this was the homework number 1, which was asking you to essentially understand how make files are used, right? So essentially, we will produce a bunch of object files, right? So this is clear with the make file. Or maybe you use a different build system. Maybe it's your Microsoft Visual Studio, or maybe it's a CMake, or maybe it's something else like a cargo, right, on Rust. But the essence is the same. So you produce a bunch of object files. And then what happens is that you say, look, my goal really is to produce this main file, right? It's my binary. I don't know, maybe give it a better name, but let's call it main just for now. And you say, look, I will invoke a linker, LD, with some flags. And what this linker will be doing is that, imagine this is the cloud which contains this linker, right? It will take all these object files which the C compiler produced, right? And will merge them together. And moreover, if it will find some unresolved symbols, something like, imagine inside your main.c, you are using something like printf. And printf is defined inside one of the system libraries, right? So maybe it's inside a static library, which is sitting here on disk, which is called, I don't know, libc.a, for example, right? And remember from the lecture last time, you understand what it is. It's just an archive, which contains a bunch of object files internally, right? Plus some index. And a linker says, look, okay, got it. I will just pick those symbols from those object files and again add those guys to my compilation unit, and essentially will link everything together, right? So this is relatively simple, right? And depending on how you link the program, there are 2 different options. One is a static, and one is a dynamic. So who can tell me the difference between those 2? So what is static? When I think I'm linking a static binary, what will happen? Sorry. Oh my gosh.
All the object files are in the same file?
All the object files are in the same file. That's kind of correct, but what am I going after? What's the difference versus dynamic? So what will happen with a dynamic linking?
It's at runtime, it's lazily loaded in terms of dynamic, but in static, everything is loaded at the same time.
So what you probably mean to say, and I didn't get your name, but thank you, is that when we link statically, everything is ready to kind of run, right? So this final, again, I forgot to say that, and this is what we'll cover today, that all of these files, despite the fact that they have an object.o extension, they are put inside a special container, which is called elf, right? And today our goal is actually first cover elf, right? Because I want you to understand what's going on. And those object files are also put inside the elf container. In practice, you can use different containers, right? But elf became the de facto standard. It's so flexible and so good that everyone is happy about it, right? So I will explain what elf is today. And this binary will also be placed in the elf file, and it will be given this name, let's say main, right? No extension. It's ready to run. So when we do a static linking, so essentially the data sections of all these object files, this unnamed, like let's say x.c, foo.c, bar.c, which can compile into x.o, bar, foo.o, and so on, are merged here together into a data section. And similar for the code section, it's also merged together, right? And some additional like maybe debug information, relocation symbols are also placed here in the same elf container file, right? But however, in order to load this file in memory, and this will be your homework number 3, like a simple part of the operating system, when you essentially invoke something like exec, right? And you say, well, please invoke my main. Internally, operating system will look up main, we'll understand that it's somewhere on disk, right? In the L file. We'll create an address space of a process. Let me change the color here for a sec. We'll create an address space for this process. Let's call it blue, right? It will be process P1. And we'll essentially load those sections in memory. And there will be, for each section, the ELF will contain, when we were linking the file, we could provide an argument, something like, say, please link it, the text section, this is T, at address OX0, for example. This means that if your binary will be, your text section will be compiled in such a manner that if you loaded it at address 0, everything will just run. All the symbols are already resolved. If you if you call something like printf here, it's already like has a correct address. So you just can simply copy this, just load it, read it from disk and place it in memory, like the text section here and the data section, for example, over here, and everything is statically linked. You have additional option. If you have relocation symbols here, this part of exec inside the operating system can load instead of address OX0, it can load at address maybe OX, I don't know, 1000000, for example. And you have enough information to patch those relative addresses, right, within a binary. But this is static linking. Versus dynamic linking, okay, who can tell me what happens during the dynamic linking? You already told me. What you said is that, okay, look, instead of like merging all these object files, too bad we don't have undo here. Instead of merging all the object files together, right? Essentially, okay, let me just take it back for a sec. What happens is the following. Let me again change the color to make sure that it's like something different. So for example, green. So those guys will still be merged, and dynamic linking will still produce like a main executable on disk. It will be much smaller because it will only merge data sections, those green things, and the text sections of this green object files, right? Imagine those are all green, right? But it will not touch those, let me change the color again, will not touch this, let's say, orange system libraries, right? So nothing like this will be linked into this file. So this will be, sorry, it will not be merged there, right? Oops, sorry, trying to draw carefully. Instead, what will happen is that when you execute exec, right? And you also pass main as an argument. So this file will be much smaller compared to this one, right? When you pass, when you execute, when you invoke the exec system call, the operating system will create an address space as well. However, it will realize that if the main was, for example, calling something like printf, this printf is still unresolved because maybe it's part of the libc.shared object library, meaning that it's a dynamically linked library or a dynamically loaded library which sits on disk. And in order to essentially start this program, before even doing that, we have to first load this main in memory, right? We have to load the data section from main memory. So imagine this is text and this is data. However, those libraries, they can be mapped in memory. So if it's the first time, some physical memory, and let me change the color to represent physical memory, let me make it gray. So in some physical memory, this libc will be loaded, right? So this is libc. Again, it's text and data sections, right? They will be loaded. And the operating system will say, okay, look, I know that I loaded once, but I will be mapping it multiple times in different processes. So if this is P1, I will first map it into P1, but then I will be mapping it into P2 and P3. And so what will happen, it will just map it somewhere here, right? So the physical pages will be allocated only once, but this text and data sections will appear in the address space of the program. And at this point, what we have to do is obviously, so we have to resolve those symbols, right? So, and there are two main strategies for doing that. So you can resolve it at the moment of loading. So essentially say, look, I will replace all the call sites with actual address of printf, and then everything will be running. But it's not how it's done in modern operating systems, right? So if you watch the lecture until the end, you notice that the libraries are using position-independent code, right? And there is this specific construction which is used, which is called global offset table for global variables, and a procedure linking table. Procedure linking table is used for linking functions like printf, right? And now you understand. So essentially, when you first invoke the printf, the code goes through the PLT, resolves the address, and then essentially places the correct value in the GDT, right? And then essentially, when you call the second time, you read the correct address from GDT and jump immediately to the function, right? So this is essentially kind of a 10-minute overview of what we covered in these 2 lectures. And essentially, I want you to remember this slide. I want you to understand. I mean, I don't think I will be asking a ton of questions about it, but okay, you will have a homework number 3, and then I will be asking questions about homework number 3. But what I wanted you to do is this: essentially make sure that you understand it for your professional life. So if anyone ever will ask you, okay, can you debugging your code and you single stepping assembly and you seeing PLT, you say, look, okay, got it. I understand what's going on. It's just resolution of the symbol. We'll resolve them lazily. First time we're going to jump through the resolver, and then the second time we'll go to printf, right? So I want you to understand how it works. I want you to understand the difference between static and shared libraries, right? Again, for your future career, because it's just not okay to not know this, right? Okay, let me stop here again for a second and prompt for questions.
How does the loader knows the address of the virtual address of the library that it is where it is being loaded?
Hold on, like I was able to hear you quite well, but then you said, how does the loader knows the address of what?
Address of the object files where it is loaded. As in case of PLT, it has to the loader resolver. I mean, the resolver has to resolve the address of the like absolute address of the library where it is loaded, right?
Okay, good question. So essentially, what you're asking is that how does the loader, which runs inside the process at this point, when it essentially sets up the PLT and everything? I guess it just, I mean, it's a great question, and I don't know exactly the answer because I never looked myself, but I'm guessing that it has essentially, there must be a collection of system calls which allow the loader or interface to the operating system kernel to ask a question. Okay, I'm looking for the library, which is libc, for example. Do you have it already loaded in memory? And the answer may be yes or no. At this point, it says, okay, look, I know that you loaded it, but can you map it in my address space? So I think the loader itself, which at this pointer, the way I was telling the story, I was saying that the loader is running inside the kernel as part of the exec system call. In practice, loader will be injected into the address space of this process. And this is briefly covered in this lecture, which I assigned you to watch, right? And essentially, this guy will be running here. And what it will do is it will say something like, okay, it will tell to the operating system, please map libc at this address A in my address space. And it will get mapped. And this way it will know the address A, right? And then we'll be able to essentially do the job, essentially. It will have the elf header as well. Everything will be there, and you will be able to essentially look at the text section and the data section and link everything together. But again, I'm guessing at this point, I didn't look, I looked a couple of years ago and now I don't remember simply, but along those lines. Is that what you were asking?
Yeah.
And I think I'm linking a very in-depth, detailed blog posts from my lectures, which essentially go kind of syscall by syscall, explaining how loader works. But again, the better way is to take a look at the binutils sources and just figure out what's going on there. but I haven't, I should admit. And x86 doesn't use it because x86 uses only static linking.
Okay.
So it's a little bit beyond the scope of this class, let's put it this way. But again, I Gary, for your professional life, it might be important. So if you need help on that, just ask a question on Piazza or show up for the office hours, and I will try to sit together with you to understand. Any other questions? Okay, all good? Okay, let me cover one thing which was missing, those object files and how we actually store them. And maybe some of you just essentially watched it because it was also recorded, but maybe some of you didn't. So conceptually, those object files, they contain five kinds of information. So essentially sizes of the section, so essentially code, text, data. So essentially, and there will be a header, which will be pointing to like offsets, or just will be just, if it's very, very static format, we'll just give the sizes, and then you will have to get, like not guess, but make sure that, okay, one is after another in a specific order, so you can figure them out, right? So essentially object code. Relocation information to essentially remember this list of places which require relocation, kind of like X, FC, FF, 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 which are currently kind of loop backwards, right? But you say, look, it was unresolved, right? So we have to essentially either resolve symbols, or if it's already resolved, you say, well, it's a call, but it's not a relative call, it's an absolute call with some address. And then this relocation information will say, if you want to move the binary in the address space left or right, then you have to patch those addresses, right? Because those are absolute addresses, right? And then like the list of symbols defined by this module, so you can export them, and the list of symbols which have to be imported from other modules, right? Because you might be like this printf, it's still unresolved in our example, right? And possibly debugging information, right? If you want a single step and see the source line which correspond to the current instruction pointer, this is generated by the compiler. In compiler play, there are specific formats for how to keep this debug information, and so essentially it's there also in this object file. And the simplest, or kind of like a historical format for object files, is called out, right? So that's why the compiler generates out file, or today it's still an elf, right? But just the name is out by default. And it had exactly those things. So it had a header, it had a text section, data section, and other sections like debug information and stuff. And if you really wanted to just load out, this is the definition of the header in C. So there will be a magic which allows the operating system to confirm really that this is an out file. And then the size of the text section, because okay, they have fixed order, right? So essentially first text, and you have a size plus header, then you will get to the data. BSS sections, symbol table size, right? So resolved and unresolved symbols. An entry point, essentially where do you have to, when you load it in memory, where do you have to put it to jump to? And then text sizes of text relocation sections and data relocation sections, and they are kept separately here. However, out, like I just make an example, like I talk about it just because I want you to understand that it is as easy as that. So just like nothing really magical happens here. So you can like understand pretty simple what needs to be done to load out, right? So essentially you say, look, I will take a file from disk. I will first read the header because I need to understand the sizes, right, of other sections, right? And then in the address space of a process, I will essentially allocate memory for the code of the program, and essentially just I will take from the header, I will take the text size, right? From the header, I will take the data size, right? Allocate space for the data for the BSS section, right? So BSS is just the size, and then it gets initialized with zeros, right? Because we don't keep BSS on disk, right? Because we know that those variables initialize to zeros anyway, right? And then essentially just copy from disk to memory, right? With just operating system just reads an inode or whatever interface it has internally. Maybe it's not an inode, maybe it's a higher level file API, but it's okay, right? It doesn't really matter. But you read it inside the kernel, put it in the address space of the process, and then essentially construct the the process registers, so the instruction pointers points to the entry point of the program, and then you allocate the stack. If the program takes arguments, which main usually does, right? So essentially, you will allocate those arguments on a stack, configure the ESP register to properly point to the stack, right? At this point, all the other registers can be either uninitialized or, depending on the standard, maybe it's zeros, right? And at some point, you can start running this process, right? So it will start executing the main logic, will be able to access the passed arguments on a stack, right? We'll execute additional system calls like sbrk, which will grow the heap of the process, right? And then, like, when you will be invoking malloc, it will be allocating memory on a heap, right? So at a high level, let me stop here again. Is this clear how you can load an out file in memory? Because we're soon going to do it, but at the level of, like, at the lowest level of details. Are the addresses in the ELF file virtual? Yes, they are virtual, because no one will, at this point, no one will be patching the addresses. Okay, I said that, and let me take it back a little bit. I mean, again, it's at this point, it's a little bit tricky to ask about virtual versus non-virtual, right? The addresses which are there, imagine you have a move instruction, you move something inside the EAX, let's say from something from address like X50, goodness, 5005, right? Oh, cannot write, right? At this point, it doesn't matter whether it's virtual or physical. The CPU will just blindly access this address. If it's a virtual address, if the page tables are enabled, this address will go through the page tables and will be converted from virtual to physical, right? But I will get you a little bit more details, and we will come to this today. Even before becoming virtual, this is actually a logical address, and we'll first pass it through segmentation. And segmentation will produce a linear address. And this linear is kind of like a synonym to virtual on Intel, right? And then this linear goes into the page tables. And if neither segmentation nor the page tables are enabled, it will be just sent to the memory, right? And at this point, you can say, okay, this is a physical address. So depending on how the operating system configures the execution mode of the processor at this point, before starting this process, whether the page tables and segmentation are enabled, then this address becomes such and such. But in 99% of cases, it will be, as we said, it will be a logical address which will pass through segmentation, will turn into virtual address, or also known as linear, and then it will be forced through the page tables, and then we will resolve into a physical address, and then this address will be sent to the memory unit, right? So, and today we're going to actually start segmentation and paging, so it will become much more clear what I'm talking about. Are there any other questions? Okay, and out was good, but it was a little bit kind of outdated because it didn't allow keeping all of these files. Remember, I was saying object files, static libraries, shared libraries in a single unified format. And that's why essentially another format was created, right? And this format is called ELF, or it stands for executable and linkable formats, essentially meaning that you can both keep executable files and object files, which can be linked, or even shared libraries, which can be relinked together by the linker and loader, right? So it's a single unified format. And you will have a homework, homework 3, in which I will ask you to build a very simple loader, but essentially you will have to read the ELF file from disk, load it in memory, right? So let's take a look at what this ELF is, right? So ELF is designed to essentially keep any kind of object file. So just relocatable object files, which are produced from C files by the GCC compiler. Relocatable means that there is a relocation information and we can move them up and down and link them again, right? Static libraries, The static library itself is an archive, right, with an index, but internally it will contain just object files, right? And those object files will be ELF files as well. So this will be an ELF. Each of these will be an ELF as well. The shared library as well will be an ELF. An executable file, which will not have an extension typically, like bin WC, which we were talking about, it will also have an ELF, right? It will be kept as an ELF file, right? So it's very convenient to have only one format which can represent each of these different scenarios, right? Okay, so what is this ELF file? Again, similar to AOut, it has a header, right? So this is the header. And header has such things like sizes of the header itself, versions of ELF. But what's important is that ELF contains 2 pointers, right? So it will have a pointer to the program header table. So what is this table? It's just an array in memory, right? It's an array of variable size, and the header will contain the size of this array, so you will know how many entries are in this array. And the second pointer is to the section header table, right? So, and that's yet another table, yet another table can be of different size, right? And typically it's placed at the end, but it's strictly not required, right? The point is that ELF is used both by the loader. So loader essentially is designed to load the program from disk to memory of the address space of the program and start running it. This is the loading, right? But also by the linker. And linker, remember, merges multiple ELF together on just moves and says, okay, you're now linked to run at address 7C00 versus 0, right? Stuff like that. So one of these tables, or this program header table, is used by the loader. And I will explain in a second why. And the other table is used by the linker. And you can kind of guess that this table contains information which is required for loading, but not for linking. So essentially just, it tells you, okay, this is what you have to read from disk, place in memory, and run, and everything will be just all right. And the section header table, and I mean, the names are annoying as hell. I cannot remember them myself. So it's like program header, section header. What does it mean? Forget about it. One is like for loader, one is for linker. I would rather say, okay, loader table, linker table, but no. Maybe there was a good reason for why to come up with those names. Even the names, like one of those are called segments, and another representation is called sections. Good luck to you remembering it, right? I cannot, but okay. Like semantically, it's very easy. I will explain what it means. You don't have to remember. Just remember what it means, and you will figure it out on the fly when you talk about it or deal with it, right? Okay. So what these 2 different tables are, right? Let me just give you an example of ELF header first. So here what I'm doing is that I'm using the GCC compiler and saying, okay, please compile, but don't link the file. I say, do not generate position independent code. Please use static linking, so link everything statically, so it's ready to run. Do not use built-in libraries like libc, because only for the reason typically you would do that when you compile something like an operating system kernel or a bootloader, because libc will try to invoke a system call, right? But there is no system call. So suddenly if you're suddenly using printf and it goes there, you will crash because it will go to some address which is may not be even present in memory, right? But here I'm doing that just for the reason of generating a very small example, just to avoid the complexity of built-in libraries, which will get sucked into this ELF header and ELF file. I say, okay, include the debug information and please use the GDB format, because there are different formats. Generate a 32-bit executable, and do not omit frame pointers. We know what these are, and use this hello elf.c file, which is they are linked from the class web page. So you can repeat this example and just see how it looks. And then I use the loader linker saying, okay, please compile a 32-bit executable, use main as the entry point, and compile it, link everything to run at address 0. So the text section should start at address 0, and the main, in this specific example, main will actually happen to be at 0, but it might happen a little bit lower, but the binary is still linked in such a manner that if you load the text section at 0, it will run. And specifically, it's useful when we will be doing something like building a bootloader next week. We will be saying 7C00, and this is where the BIOS will load the first sector from disk and will place it at this magical memory location. That's just a convention between operating system developers and hardware developers. And you have, if you want your bootloader, boot code run correctly, you have to link it to run at this address 7C00, and actually don't use built-in libraries because there will be no libc, right? So, but again, here it's not super critical. I'm just using it for the sake of example. I say, okay, please produce a out of this hello-elf object files. And if I use this tool, which is called readelf with -a flag saying, okay, show me all the sections, this is what I will have. Like the magic will be the specific magic number, which confirms for the operating system that the file is actually an ELF file. It's not a mistake. It confers some information, contains some information saying that it's actually a 32-bit executable, like yada yada, uses different formats, little endians, stuff like that, right? Versions. What's important here is that the entry point address, remember this entry, which is main in our case, is actually happens to be at address 0 in this. Like it has to be close to 0 because the compiler can place main after another function. And just in this example, it happens that the main is first, right? But it's okay. This is the entry point. So this is here. This is where the EAP should be set to run this binary, right? The program header tables starts at byte 52 within a file, right? Because header can be variable size. And a section header table starts at the end, remember 2980 bytes into the file. Size of this header is 52 bytes. Size of the program header is 32 bytes, and it contains only 2 entries, right? So this first table, which is at the top, which is used by the loader, contains only 2 entries. And the size of the section table is 40 bytes, and it contains 15 entries, right? Okay, so you kind of get a feeling that everything what I described is actually can be like listed with this readelf, right? So everything will be just fine. And okay, 2 views, one for the loader, one for the linker. Remember that loader, in order to run the program, it will essentially, the linker might generate multiple sections, like section for initializing the data. Remember, you just watched the video, right? So you know what it is. So some like library initialization or class initializers, which have to run before even main runs, right? Or maybe it, and separately, there will be a text section, and maybe there will be some other sections, but all these sections have to be loaded. That's why for the purposes of loading, they're just bundled together here. It's just one entry in this program header table, right? You say like everything what is executable just be together. So this, we can just copy it in memory of the process. Internally, there might be like multiple sections, but we don't care because the loader is a simple thing. It will just set this memory as executable. Like in the page table, it will mark them as executable and it will run. Like that will be okay. Similar for data. So you say, look, if there are multiple sections, I only care about which one is writable and which one is readable, read-only, right? And so essentially, writables will be marked as write and read flags, and read-only will be marked as read-only in a page table, just to protect read-only variables, right? But even GOT is like, GOT is actually loaded, right? So I should have probably included it, right? But that's the point. So the point is that everything is bundled together for the loader view. And the linker has a slightly more fine-grained view. In this example, I use blue colors, meaning that it can distinguish each individual section, right? Because this is segment and this is a section. Each blue section can be used differently for linking. So it contains a little bit more of a fine-grained information. So it knows where the relocation symbols are. I'm not even like, they are not in this example, but there will be like a relocation section for specifically for relocation symbols. There will be a debug information section, right? Because, okay, cool, you compiled and this information is on disk. It will never get loaded in the address space of the process because the process doesn't need debug information to run unless you, again, like support some kind of a runtime debugging when you can attach to a process and everything will be still there and you want to keep those symbols around. But maybe you want to actually keep them somewhere separately. You say, look, I will have a separate repository which my operating system will maintain, and I will put those symbols there, right? So it's totally fine to do that as well. moreover, this way, you know, if the program crashes, your symbol tables will not be overwritten by that crash. You know that they are intact, right? So like not symbol tables, but debug information. So it actually makes sense to do this, right? So, okay, so you do this, right? So you got the point. So the linker, if you want to relocate the file, moving it up or down, like up or down, relocate not the file, but this object file, right? You can do that, right? You can link more, and then like you have enough information in this table, and this information is used by the linker, right? Let me stop here again for a second. Are you clear on how it works, or like have some understanding about it at this point? Anything? All good? Okay, so this is ELF, and the reason I was bringing it up is because you will have a homework on it, right? So I wanted to make sure that you understand what's going on. Again, just if we scroll down, same kind of command. If we scroll down and say, okay, wait for the program headers. As I said, there are two entries. There is like one which is loadable, right? So it's a very simple, since we build everything statically, everything is bundled together. So like in this example, actually, like even text, data, read-only data, and everything is bundled in one single loadable section. And again, it's just for simplicity of this example. In many realistic examples, you will have multiple different sections, but here you say, look, load this at virtual address 0 because we use this 0, right? Remember, and this section starts at byte x74 inside the file, and mark it as RW, read, write, and execute, right? Because everything is bundled together. This is not how the real operating system will do it, but for the sake of this example, this is how I compiled it, right? Is the executable segment read-only? Right, so normally in modern operating systems, it's actually, it might not be even read-only. It's like, I think modern CPUs support the mode in which you can only execute. You can't even read, because reading could reveal some information about the binary and might reveal some attack mitigations, right? But typically, at least normally today, it's either executable or writable. So typically you can read the section which you execute and you can execute it, right? But you cannot write it, which prevents a series of attacks which essentially modify the binary on the fly, right? But it didn't used to be this way, actually, to be honest. It's recent, in the last 10 years, when the people, you know, the attacks are on the rise and people started coming up with more and more sophisticated attacks. Operating systems started to deploy more and more sophisticated defenses. They still don't work, you know, everything is exploitable, but besides maybe formal verification and stuff like that, but it's harder to exploit, let's put it this way. What is the physical address in the program header used for? Does it try to assign it to that physical address? Actually, to be honest, I don't remember. I don't think it will try to assign. I don't know why we use physical and virtual here, but that's a good question. But essentially, you will be using this address, the virtual. I can look it up for you, though. That's a good question, and I should know the answer, but I don't. Maybe ask on Piazza, and I will answer. Any other questions? Okay, good. Just two sections. And to be honest, I don't even know what this GNU stack is. It's some convention on Linux, right? So, but only this section will be loaded by the loader, right? I don't really know what the purpose of this GNU stack is. Some specification of what needs to happen on the stack. So specifically even this alignment requirement. Remember, everything is aligned, 16-byte aligned, right? So it will request the memory to be 16 bytes aligned. And this is like, has to be 4-byte aligned. Right. If we take a look at the section header table, which contains the sections for the linker, you will find this information, like, not surprisingly, right? So by convention, one is null, empty, program text has to be loaded at address 0, starts at offset 74 inside the file, such as such size, right? Read-only data, right? EH frame, ELF header frame, don't remember what it is, the data section, BSS section, again, don't remember what comments are, a bunch of debug information sections, right? So probably split into multiple sections for whatever, symbol tables and string tables, again, used for resolving undefined references and for references which are exported by the file. And we don't have any relocation information because we build everything statically. So essentially, you said, okay, hold on, like this file will not be able to, we will not be able to relocate. So we said it's compiled and linked to run at address 0. No, not compiled, but just linked it to run at address 0. That's it. So we stripped out the relocation headers and the linker will not be able to move it in the address space. So it has to be loaded at address 0 to run, right? But in a normal file, in which you will omit the static flag, you will have the option of saying, or even with the static, I think you can pass a flag to say like, please keep the relocation information around. So later on, the operating system might shift this binary. But that's essentially the high-level overview of this ELF. And there will be a homework in which you have to dive in and like essentially you will have to read the header in memory, then iterate through program header table, loading this everything what is marked as loadable in the memory, and essentially we'll have to jump to the entry point of the process, not the process, but this file, and it will execute a simple function. Okay, so this is the end of this kind of these 3 lectures of unlinking and loading, right? So we learned a lot, and I hope it will be useful in the future for you. But now I will stop for questions, for final questions, and we'll switch to segmentation and paging, which we have to start today. All good? Okay, so now we're back on to something new, which is even more exciting, to be honest. Everything is even more exciting in this class. Let me start a slideshow. So, okay, again, we're getting close to boot into main, boot our tiny operating system. But before booting, we have to understand the basics of address translation, because CPU starts in real mode, right? And the bootloader will, depending on again on how it's configured, will typically leave you in a real mode as well, for historical reasons. At least the bootloaders which I'm covering in this class, and then we will be looking at something like essentially skip the bootloader. It will be BIOS, which reads the boot sector, which we will compile ourselves, which is loaded at address 7C00. And this guy will read the operating system kernel from disk, right? We'll set up segmentation and pages. And then essentially everything will jump to the operating system kernel, right? Everything will start running from there. But in order to do those steps, right? So essentially, we're not going to cover the BIOS. So I will explain how it works. But these components we have to develop. So, and we will cover them in this class. They are part of the x86 operating system, right? But before doing that, we need to have solid understanding of what segmentation and paging is. So, and let me of course ask you a question. So, what is segmentation? Who can tell me? Anyone? I'm pretty sure like you guys, you've heard these words, right? So you've heard the word segmentation fault, right? That's how the program crashes. Grouping every 4 bytes, not quite. Okay, segmentation is a little tricky. And I mean, not many people cover it in the operating system class. Everyone just says virtual addresses and forget about segmentation. I still believe it's important just because I want you to understand how machine boots, how everything is set up. I mean, I skipped a bunch of I will skip a bunch of low-level details. And I mean, to be honest, I don't even know everything, right? But I guess I'll give you a chance to understand it if you need it, right? I mean, why is it important for security purposes, even like how the environment is set up, all the execution protection mechanisms and how they are set up by the operating system, by the loader, by the BIOS, right? So you need to understand how everything works. It's a little bit painful, but it's not as painful as people usually say, right? So bear with me. Okay, let me provide some initial motivation for segmentation, which comes roots back, decades ago. Remember this introduction lecture, and I was quickly scrolling through the slides, but the idea is that you want to run two programs in memory, right? You have one memory. Imagine this is your physical address space, which is backed up by, DIMMs, right? How can you do this, right? You say, look, guys, this is main of one program, maybe it's WC, and maybe this is grab, and it's main of grab. Can we somehow share the memory which we have between these two guys? Does anyone have an idea how to do this? Any ideas? No? Come on. Well, remember, we know what relocation is. I will ask you a killer question. I will ask it on the quiz, right? What is relocation, right? Okay, people are yelling. Like a simple argument not to yell doesn't work. Remember relocation, right? So you say, look, well, we got the point. Like you have two binaries, just stay like nothing wrong can happen. Let's take two binaries. One is WC, which has a text section and a data section. Let's link it let's link it as a static binary, and let's relocate it to run at address 0, for example. And why not to place the second address? Let me just yell at my kids just a sec. Okay, sorry about it. So you say, look, okay, hold on. This is WC and this is grab. And you say, why not? I will relocate grab to start at address, I don't know, something 1000000, right? And there will be a data section, and that's it, right? So this will be calling, this will be calling functions from its own code section. This will be calling functions from its own section that actually will work. Do you believe that it will work? They will have their own stacks. This is a stack, and this is a stack, right? This seems like a viable solution, right? Agree or disagree? Yeah, believable. Again, remember, power of relocation. Just again, an operating system doesn't have to know these addresses in advance. All of it can be linked to run at 0, but when you load the program, you just do the relocation and shift it to some space which is still available, right? We lost a couple of properties which we wanted to gain, right? So what are those properties? What is bad about this solution? What do you think is wrong? We need a continuous chunk of memory to run. That's true, right? And you might have some fragmentation later on. But even without continuous chunks, we seem to be fairly, let's imagine we have enough memory. Anything besides continuous chunks. An important property of a program is isolation, right? In this specific scenario, if you suddenly make a mistake in your program, and instead of reading your own data section, you read data section of another program, That's bad, because maybe this is sensitive information, like your bank account, and you have temporarily you typed in the password and it's stored in some data structure, right? So ideally, you want to build some kind of an isolation boundary between these two guys, right? Agree with me? Okay. Let me just again. Let me just yell a little bit more. Hopefully more success this time. Okay, so this is the illustration which illustrates the same example. Like again, just relocate, we know it may run, right? So relocate at this address. As I was saying, what's the problem? There is no isolation, right? As I said, so one program can accidentally access data of another program, as I was just explaining. It can read and even write the heap of other program, right? It's worth mentioning that isolation can be enforced in software. I don't know how many people heard about software fault isolation techniques. Who can name me a project which is very popular today, which uses software fault isolation? And maybe someone knows what it means. Anyone? Do you know Docker? No, Docker is different. So WebAssembly, WASM, and Google Meta-cle, essentially the idea that you can run the C code in the browser. It's exactly this idea. So idea of enforcing this binary, this isolation boundary between the process. So how can this be enforced? So for example, when you do a move from an address, maybe it's address A, right? Or A, you can probably just check statically, but let's say we use a different, like a register, EAX, right? And we load from this address into the EBX, right? You say, look, what if the compiler will inject a tiny check in front of every move instruction, checking that this EAX address is within the boundaries. So something like from 0 to this address, right? In this example. And this is roughly the idea of how you can enforce isolation boundary in software, right? So this is essentially at a high level, this is what WASM is doing, right? And WASM is very popular these days. It's like it became a growing standard, so essentially, which allows you to run binary code in the web browser. And the idea is that you essentially change your code according to a set of rules to enforce the checks in front of every move instructions, which access memory, and for example, in front of every jump instruction, so you cannot jump between the segments. And also there are some additional rules to make sure that you cannot jump in the middle of instruction and stuff like that, right? And Docker is a whole different story. I will try to explain by the end of this class what it is, right? So roughly speaking, you say, if you enforce this, if you use the software fault isolation technique and it's generated by the compiler, so you just essentially you change the GCC compiler, kind of adding an additional pass, which says in front of every instruction, which can break isolation, and I will enforce a specific check. And it's a sequence of assembly instructions, but you can think of it like as checking if the access is in bounds, right? OGS engines running on web browsers, OGS engines, JavaScript engines, but those are different things. JavaScript is essentially, you take a JavaScript and you use a JIT compiler to compile object code. Imagine you have a Quake or Doom, essentially, this is your favorite Doom game, and you say, look, I want to run it in a web browser. It's written in C. Compiler can still produce the executable, and then this SFI can make sure that it's safe to run Doom inside a browser process in this container, in this segment, which is enforced by SFI. Okay, maybe it's again outside of the main topic of this class, but I just wanted to make sure that you at least understand what's going on here. However, you got the idea. So relocation is a powerful technique, but isolation is missing. You can enforce isolation in software. Of course, that will incur some slowdown because you have to do those checks, right? It runs a little bit slower, but you're kind of getting this idea. So you say, okay, look, what if those checks can be done in hardware? What if the hardware provides the same mechanism saying that, look, I will introduce something, what I will call a segment, and I will be checking accesses, right? Essentially, if you try to call a function, I will not let you go beyond the segment. If you're trying to move or access memory, I will not let you go beyond the segment, right? So this is idea, essentially the original motivation for segmentation, right? And moreover, back then, it had a second flavor. You don't even have to relocate, right? Okay, so as I was saying, you're asking for this hardware support, right? Hardware will be enforcing those segments. And now we're entering segmentation. So what are we aiming for? We want to isolate and provide isolate execution of the process or execution of a program and provide an illusion of address space. Why illusion? Because then you don't have to relocate every binary. So every binary will have its own private address 0, right? So you say, okay, look, how we can achieve it? Well, very easy. So here we have two processes. Maybe it's even the same binary, right? Process 1 and process 2. And maybe it's the same ls. We just invoked it twice. And this is the physical memory which we have on the machine. So roughly speaking, what the hardware will be doing, it will be converting all the addresses. So if you're trying to, for example, to access address 0 in this process, the hardware will add some constant, which is called the base of the segment, right? And essentially in physical memory, will be accessing the address, not x, but x plus base, right? And this base is configured by the operating system. The operating system says, okay, look, I will take all available physical memory. I will let one process to access this range of physical memory and will let the other process to access this range of physical memory, right? And I will choose bases in such a manner that they don't overlap. So, right? So there is no way for process 2 to access any of the green memory because even address 0 will land it here, right? So, and can read more. And you say, look, there is a size of the segment, so it cannot go beyond. So this will call a segmentation violation and an exception, which will be delivered to the operating system. Operating system will kill or terminate this process, right? Okay, so idea is very, very simple. We're just adding this basis, right? Are there any questions about this main segmentation? You agree that it will work. So essentially, you don't need to relocate anything. Everything can be statically linked to run at address 0. And this one will also run at address 0. The hardware would just add a base and enforce the limit, right? And then the green can access green memory, yellow can access yellow memory, right? Agree with this? Okay, so far so good. As I was saying, so there is one problem. Where do these base addresses come from? Remember, base 1 and base 2. So what do you think? Where will they come from? Because we don't have like a register to keep a base. You may say, okay, let's introduce a register, right? Or what would you do? In memory, data structure to track it. Exactly. I don't know, Surya, whether you know it or you have a good intuition, but correct. Why is that in memory? Because we might have hundreds of segments. At least we used to have back in the days. Today, we don't use that many. So today, as a register will do. But technically speaking, it's a combination. Like we'll have a table in memory and we'll have one register, which will periodically keep the current segment, right? Okay, so the hardware can maintain a table of base addresses, right, in memory. One base for each process or one base for each segment inside the process, but typically it's for each process. And dedicate a special register to keep an index into that table. So the current, essentially, the table is in memory and the register code segment will be used as an index, roughly speaking, but it will actually read this entry and will cache it somewhere in some other data structure on a CPU, right? Temporarily. And the way it looks is like this. So there is the table is called the global table or global descriptor table. This is how Intel calls it, GDT. So there will be a selector register, which is essentially an index into this table, right? And then this will contain the base and a limit, right? I only illustrate the base, right? So in this example. So and this base is when this selector is used, the base is read by the CPU, and this base will be added to all the addresses. So essentially, if you have something like OX5 load into EAX, right? Instead of like really going and loading something from OX5, we will add the base and we'll load from this physical address, right? Agree? So far, so good. Very simple, right? Okay, let's add a little bit of details. Yet another example with just the one which I just drew. So again, this one uses an AT&T assembly. So it uses from the memory pointed by the EBX register into the EAX register, right? So EAX is 0 at the moment. EBX is this address 300010, right? So it contains the value x55, for example, since the base currently is this address 110000, right? The base is added to the address, this plus this, right? You land on a physical address 410010, right? And this is where this 55 is actually contained. So this is the physical memory, and this one, you can call it a logical address space line, right? Logical. I will explain why it's called logical in a second, right? For the second process, which accesses the same address, so it uses the same address 30, same as here, right? Those two are the same. Since the base is different, it goes to a different physical address. This example is 810010, right? Because we added this base to this address, right? So simple addition here. And here we contain the value 56. So these two different processes, they have virtual at this point, or logical as it's properly has to be called here, address spaces which can have two variables, and in one process the variable contains 55 and another the variable contains 56, right? Just with the segmentation. And the hardware implements this logic of essentially adding this to every address which is used by the instruction. The base will be added and it will be checked against the limit, whether it exceeds the limit of a segment or limit of the size, right? Good. Okay, so what we have now, so segmentation, so the address now consists of two parts. So one is the segment register itself, right? This is the index into the table, and the actual error and the actual value in the register, right? Right, which we're using, right? But first, like this index will always choose an entry in the table. So in this example, the entry 1 is chosen, right? So this global descriptor table is the proper name for this table in memory. This table is actually located in memory, right? So it's allocated in memory of a process, and there is a special hardware register which is called GDT register. So the register which contains the physical address of the global descriptor table, right? So this example is at 7095. So this is exactly the table which Surya was suggesting, right? And here we have a segment register which says, okay, please use the segment number 1. Hardware goes into this table, picks up the base. Remember, this is the base, and essentially to this address, the base is added, right? Plus, and we will land on this physical address, right? For this process. And when you do a context switch, for example, the operating system might either change the global descriptor table register to point to a different memory location, and then the process will be using a different GDT, right, with different bases, or it can like essentially it's less frequent, but you can change the index of the code segment, right? Any limit for the max size of each segment? Of course, the segments can go on 32-bit machines. They can start at 0 and can cover the entire 2 to the power 32 address space, which is 4 gigabytes, right? Correct. So the operating system, so essentially, Bumpsy is asking, okay, he's saying, or she, I'm sorry, I can't judge the gender from the name at this point, I'm sorry. The operating system, he or she says, okay, look, the GDT can accidentally overlap with the segment, right? you have to be careful as a designer of the operating system. When you create a new process, you have to make sure that the segments will not overlap with other segments, with other addresses of other processes, and with GDT and with the kernel itself, right? So you have to be careful, but we will see how it's set up in x86, so you will understand how it's actually done, right? Any other questions here? Okay, so as I was saying, very simple transformation. Base comes from the global descriptor table. We add it with the address. The resulted address is sent to memory controller, right? This is the physical memory. And this is done in hardware, in silicon. So essentially the logic on the CPU just does this transformation before even sending this address to the memory unit, right? Okay, so this is an example here. Again, we looked at it just before. And typically, as I was saying, each process will have a private GDT. So here are two processes, one is yellow, one is green, right? And the operating system, when it will be doing a context switch, switching from one process to another, will reload this with this register, GDTR register. And it's a privileged instruction. So essentially, the process cannot simply say, okay, look, please load something new into this register. It's not allowed because segments also can encode the privilege level ranging from 0 used by the operating system to 3 used by the user processes, right? And any code executing at level 3 is not allowed to execute those privileged instructions which change the global descriptor table register, right? But essentially here in this example, yellow process has its own GDT, green process has its own GDT, everything is fine, right? Okay. And so the GDT will have the base address and the base address at the end and the limit of each segment, correct, and some additional flags. And we will take a look in a second, not today probably, at the entry, at the exact format of the GDT, right? You're correct. So now this new addressing mode is called logical addresses. Well, who knows why Intel calls whatever, everything, but essentially it contains of two parts, as I was saying, segment selector and an offset in the register, right? And this is from the Intel document. So if you read the Intel document, you will see a similar picture. It might be updated with some blue colors, but the essence is the same. So this is the descriptor table. This is used as an index. It only has 16 bits, right? This, which limits the number of entries in the global descriptor table, right? So it reads the segment descriptor, gets the base out of it, plus some flags like whether it's executable or, for example, only read-only, and then adds it with something what is inside the register, and what's this inside the register is called an effective address, right? So this terminology will be all over the place in the Intel manual, and you will shoot yourself. It's a little bit hard to get used to it, right? So logical, virtual, linear, and this is effective, right? And this is what we add and we get one address, and this is called linear address. And this actual linear address will go as if paging is enabled, this is effectively becomes your virtual, right? But this is, you cannot, I don't think you can enable paging without enabling segmentation, right? So segmentation is always on Intel if the paging is on, right? You can enable segmentation, but skip the paging, right? But typically these days people always enable paging, right? So this linear address is called, typically in a folklore, like when we say to each other stuff, we say virtual, but really it's after the segmentation, right? So, and segmentation can change your virtual address. Like typically it's not done on modern systems, but it can be done, and it was done in the past, right? Okay, good. So as I was saying, go descriptor table. So each entry in the descriptor table contains roughly this 3 elements. So access bits, so some flags, the base address, and the limit, right? So limit is the size. It just Intel calls it a limit, right? And access rights can be like executable, readable, writable, privilege level, right? I will explain privilege level later, but essentially the code segment. And if you have the privilege level 0, you're running as a super user or as a kernel. If you have a privilege level 3 here, then you're running as user level, and then you cannot execute those privileged instructions, right? Okay, so offsets into the segments are in registers themselves, so something like move from EBX. So this is the effective address, right? So this is what you pick from the instruction. You load from here to here. Just remember this terminology, effective address. And the formula is relatively simple. This is what we do. We say effective address is, we're using this selector as an index into the table, into the descriptor table, and then we're picking the base field and essentially adding it with the effective address. So, right, again, worst comes to worst, it's very easy to remember, but just make sure that it's not like, right, so this is the addition. Okay, this is just the final thing here. So segment registers, they are just, they are 16-bit long, they are indexes into descriptor tables. We will be covering only one of them. There are multiple descriptor tables, but like XV6 uses only one global descriptor table, right? There is one additional wrinkle. Let me just take 2 more minutes of your time here. So segments are associated with one of 3 types of storage, right? So there is a segment for code, segment for data, and segment for stack. And typically every instruction, so for example, if you want to add something from a global data section in front of it, since it's now a logical address, you have to put the index, right? Like a data segment. If you're accessing something on a stack, you're accessing a local variable, you should put an index saying, okay, my address is not just y, but it's some index dot y, right? So, and similar, if you do a call a function, you say, I will be using a specific code segment, right? But it's just so annoying to write code like this, like explicitly putting the segment selector in front of every memory access or in front of every instruction invocation. That's why in most cases, a default segment is assumed, meaning that for a function, if you call for the instruction which does a call, it will assume that you're using a current value of the code segment, right? So, and only when you have to reload the segment and jump into another segment, then you will explicitly say this assembly instruction uses the CS and the value will be such and such, and we will call into that segment. Got it? So normally, this is just implicitly assumed that the stack instructions assume the stack segment, data instructions assume the data segment, right? Okay, so that's why typically you don't see instructions like that. It's just assumed by default, right? Although you can explicitly write assembly like that, right? So essentially, because your address now has 2 parts, remember, the selector and the offset, right? So just don't forget them. Don't forget, right? So this is the explanation that it's a little bit cumbersome. So typically, code segment, data segment, and stack segments essentially just assumed implicitly. So what did we achieve with segmentation? We have each process has an identical copy of an address space, right? And roughly speaking, we can implement fork, right? So you remember fork, we can clone the process memory. We can just create a new segment. We can create, remember you were running WC or like shell, for example, right? You invoke fork, you drop into operating system kernel, the operating system says, okay, I will create a new segment for you with a new base, right? And a new GDT maybe. And we'll just copy this here, right? And that should run because it's identical. All the addresses are resolved correctly. You just have to change the EAX register to return the 0 in the child and the process ID in the parent, right? And of course, the segments enforce isolation because you cannot even issue an address. If you issue an address trying to access something over here, you say you go beyond the limit of your segment and you will crash, causing an exception, right? So, okay, let me stop here and we will continue a little bit with segmentation, but we will mostly cover paging starting next time. So if there are any questions, I can hold, like I hang out here for 5 minutes, but if you have to run for the next class, go ahead, disconnect, and I'll see you on Wednesday. Any questions? Okay, good. Then see you Wednesday.